hear me? Yep. Thanks, Tim, for the introduction, and thanks for the toughest slot here to talk after lunch when most people want to take a nap. And I've been told I give sometimes the most boring seminars, but hopefully this data is actually pretty exciting, so hopefully you'll stay awake. But there is one boring slide we have to go through first, if I can get this to advance. And that's, a time frame which you all know of, why we're all sitting here with masks and socially distanced. And I won't focus on the upper half there because you all know pretty much, what happened from December 2019 up till now. But what I did want to point out was that I have some numbers here of like August of last year versus August of this year. Because if you compare this to the 1918 flu pandemic, where it lasts about the same time frame, about a year and a half, 2 years. We didn't have vaccines back then, and they didn't practice the social distancing and all the things we did this time around. And so back in the 1918 pandemic, the death toll was like around 50 million people. And this was back in August. We were from August 2020 to 2021, went from 20 million cases globally to over 217 million at the end of August, and about 5.5 million deaths globally, as opposed to about the same time span in 1918 of around 50 million deaths globally. So as painful as the things we did to limit spread of the virus were, it seems to have helped significantly. And in the 1918 pandemic, they estimated that about 500,000 people globally were probably exposed to the virus, which at the time is about 1/3 of the global population. And if you look at the global population today, there's a lower percentage rate, as opposed to back in the 1918 pandemic. So the other thing that really has helped us out here is the ability to quickly develop a vaccine, because the modern molecular technologies that have been used to make the protein vaccines or the RNA vaccines really sped up the process to get a vaccine developed within about a year from the beginning of the pandemic to now, which we didn't have back then in the 1918 pandemic. And even with some of the other viruses and other vaccine technology we've had in the last, say, about 20 years ago, this has helped us really get a good, effective series of vaccines out there and vaccinating a large percentage of the population, which geographically now there are some areas that, of course, are still below 50% or around 50% vaccinated. Some are getting up there into the 70s and 80%. And if you work in people vaccinated and people that might have been exposed, we're up there in some areas in like the 70, 80% people that are immune in some way to the virus. But of course, in other areas are still pretty low. But what I really want to get into is, the different approaches that we have been using, which initially, of course, the molecular detection of the viral RNA was the key diagnostic for determining if you were infected. There are a series of labs and tests you can get to do antigen detection. And of course, the serological antibody tests have become prevalent as well. So, PCR tests and some of the isothermal assays, and eventually Luminex had a couple of PCR assays to detect the presence of the viral antigen. And then as far as serology tests, early on, there were a bunch of single antigen tests that could look at either spike antibodies or nucleocapsid. And there was one that could look at spike and nucleocapsid, but it was one of these lateral flow chemistries. Eventually, Luminex built its own assay and put that on the market that some of you might be familiar with. And it looked at titers against the spike protein subunit 1, the receptor binding domain of spike, and nucleocapsid. Has a number of control beads in there to look at certain antibody levels when you add your sample. And it takes about 3 hours to run, but you can run it on all 3 of our XMAP instruments. Now, before we had our kit out, as Tim was saying, there are a lot of people that wanted to sort of build their own assay. And building these assays is pretty simple. I think most of you probably know this already about how the technology works. It's a bead array where what we've done is we've taken essentially these 3 dyes, and we can make different ratios of these dyes, and essentially we can have 500 different mixes of these dyes. So we can dye different batches of beads that are slightly different color. So these unique batches are pretty much numbered from 1 to 500, where that number indicates sort of what we call the bead ID or bead region. And so multiplexing is essentially taking different batches of these beads and hooking a capture molecule to it so that if you have something like this 100-plex where these 4 beads are, is that me talking? Oh, that's you. Oh, okay. Wasn't sure if she was asking a question prematurely or what here. I wasn't done yet to that point. Yeah. Okay. So, you can make, whatever plex you want, and these can be run in a 96 well plate, or if you have, say, this fancy looking thing over here, or our FM3D, you can run it in a 384 well plate. So the microspheres are, small particles. They have a polystyrene core and they're coated with iron magnetite. And the magic of, developing the assays is sort of through not only that ability to multiplex with the dyeing process, but having this carboxyl group, which allows you to couple different types of capture molecules onto the bead surface for either genomic or proteomic assays. And if you're new to Luminex and want to explore some of this, get in touch with your business manager and we can talk to you about how to develop different assays on this platform. So as far as the proteomic application and the serological applications, building these serology assays are actually some of the easiest assays to build. And for something like this coronavirus assays, if you're not going to generate thousands of peptides like Jim's group did, we have groups that will like to use the whole protein. And so in this case, something like the spike protein has a lot of lysine residues, which when we activate that carboxyl group with EDC, it'll bind to the amines on these lysines and couple your protein. And when you got lysine scattered around that protein, especially something as large as this, it'll couple it in multiple orientations. So hopefully all the epitopes that your immune system might see will be exposed and pick up those antibodies in a polyclonal response. If you have a smaller subunit protein, let's say the receptor binding domain of the spike, it's smaller, but it's a large enough size that it still has a lot of lysine scattered over it to, again, couple pretty efficiently in multiple orientations. And so that's what we pretty much did with the group in Rochester. So we developed essentially a 5-plex assay for this single reporter assay, which we ran on an FM3D. And we used the full-length spike protein that was his tagged, as well as the receptor binding domain of spike, which was also his tag and had an AVI tag on it, as well as a nucleocapsid. And in this coupling strategy, instead of coupling, say, micrograms per million beads and really loading up and thoroughly coating the bead surface, we wanted to have a little more control over sort of the amount of molecules we had on the beads to control the strength of the signals. So we did molar couplings where the larger spike was coupled at 10 picomoles per million beads, and the 2 smaller proteins were coupled at 100 picomoles per million beads each. Now, theoretically, this is at subsaturating levels, so the bead surface is not totally packed with protein with no spaces in between. We also included a couple of control beads. There was one IgG control which had human IgG on it, and that was just to confirm that our anti-human IgG reagent was added to the reaction. So if we saw, some low overall MFIs, in a well, this would tell us whether or not it was because of misloading of the detection reagent or not. And then we had another bead in there, what you call an instrument control bead, which just kind of monitored the MFI signal to make sure it was consistent in every well on the plate. So the next thing was that when you're building one of these assays, when you're coupling your antigens to the beads, in this case, especially with large proteins like this, you want to confirm that the antigens are coupled. So we have to use, we had antigens from several sources we tried, and we had antibodies that could detect them from several sources. So we could confirm that, when we're coupling these antigens at different amounts, different coding levels initially, we could find, that it was consistently coding at different levels and measure that level all the time. Once we were able to do that, the next thing was to determine, what coding level worked best, which was those ones I showed you, and then determine what's going to be the best detection combination for picking up the human sera antibodies that bind to the antigens. So we tested, several biotin-labeled antibodies as well as PE-labeled. And we were debating whether or not to use a sort of a biotin SAPE chemistry versus a PE direct labeled chemistry. So we played around with that, and in the end we decided on using a biotin labeled IgG with SAPE, strep avidin phycoerythrin, as opposed to the PE labeled, because this gave us better control over the amount of the anti-IgG we could put in, to fine-tune the sensitivity of that IgG concentration, and then, also tweak the SAPE so we could get the maximum brightness out without, skewing the results. And so that's the combination we went with in the end. Then the other thing was the assay, we wanted to make sure we could maintain the sensitivity as well with regards to the serum dilution. So we tested several different serum dilutions, and in the end, we decided on diluting the sample at 2000x, and it actually required less than 10 microliters, but we couldn't pipette a fraction of a microliter, so we used 10 so that we could put in a larger volume and dilute it to 2000, and that worked pretty well for all the assays for the single channel reporter assay. Then the other thing was, the lab processed a lot of samples per day and per week, and they wanted an assay that they could turn around pretty quickly and not sacrifice, specificity or sensitivity of the assay. So we tested several conditions to run the assay at, and we finally came upon this workflow that was about 45 minutes to an hour. And one of the tricks was we ran everything pretty much at 37 degrees so we can run really short incubation times using our biotin labeled antigen or antibody here at 0.62 micrograms per ml, and our SAP at 1 microgram per ml to keep all these background levels down and still have sensitivity in the assay for this short assay. So in order to determine sort of the threshold and specificity of the assay, we tested about 218 serum samples from pre-COVID patients and patients that had other types of infections. These are the different serum groups that we tested and the number of samples from each group. And on each antigen, we were looking for sort of the basal level of signal that would set our minimum threshold for each bead and give us an overall threshold we can use for the assay. And you can see here, for all of these, around 100 or a little over 100, sometimes close to 200 or 300 was some of the background levels we saw with, samples from these different types of infections. But in general, these were tested also with, all these COVID negative samples, which we then, determined was representative of our baselines to give us an overall negative result. And then we wanted to confirm this with PCR positive COVID patient samples. And we also compared this sensitivity of the assay with regards to another commercially available kit from the Abbott Architect system that only used looked for antibodies against nucleic capsid. And the other thing we did was we knew that there was going to be a change in the antibody titer over time from infection. So we broke the samples up into groups from days from symptom onset, starting from 0 out to plus 21 days. And what we can see is that we do have sort of for each time frame here, for spike, RBD, and nucleic capsid, we do see different percentages that we're picking up with the assay based on the antigen. But the spike gave us a pretty good signal, and compared to the Abbott Architect system here, this gave us generally the highest signal that we could see at the different time points. And when we compared it with the Abbott Architect system, we see that with regards to the percentage of positive calls we got from these PCR positive samples, that was pretty much out to about days from 0 to days 10, from days from symptom onset, where based on the spike height percentage correlation, we were usually higher than the Abbott Architect system. And actually, maybe even if you go out to 15 days, 11 to 15 days days from symptom onset, we're still maybe outperforming the Abbott Architect system a little bit with regards to catching these titers earlier than the Abbott Architect system did. Oops, wrong way. Okay, so now the next thing we wanted to do is determine with the single reporter channel assay is, can we detect neutralization using an ACE2 competition? And can we do it with the same assay protocol? And so what we did was we pretty much ran the same assay protocol with the modification of having this ACE2 incubation step added in before we added the serum to the beads. And we just simply did this short incubation for at least 2 minutes, shaking before we threw the serum in. So what we expect to see here is, of course, once ACE2 can bind to the antigens on the beads for spike and the receptor binding domain, it should prevent antibodies that can bind those epitopes from binding to the antigens and just decrease the signal on those beads. So we tested this with 11 clinical samples that range from low titers to high titers, where we did that ACE2 incubation, as I just indicated, with the standard 2,000-fold dilution of the serum sample. And then we looked at, how much MFI value, or was the signal value left with incubating these reactions with different amounts of ACE2. And what we could see is, as you increase the amount of ACE2 used in a reaction, you can see the signal drop, as you would expect, for spike and RBD, but it did not change significantly or at all for the nucleocapsid, suggesting that it was a pretty good measure of the ability for spike to bind any antibodies that could bind these, and probably could correlate with providing protection with that antibody titer. So the other thing we want to do is, again, kind of break it down to days from symptom onset. And so here you see days 0 to 5 going out to plus 21 days. And we're looking at sort of the percent here of residual MFI values that are left, on the 3 different antigen beads. And we can see, we're picking up pretty quickly in days 0 to 5, a drop from, the nucleocapsid on down with regards to the spike and the receptor binding domain. And as you go further out, it dropped further, but it pretty much kind of plateaued there with this particular assay. Again, though, suggesting that as we go out, from days of infection on further out, the ability to generate neutralizing antibodies happens pretty quickly. And in this case, we didn't use the 4 micrograms per ml of ACE2, we only used 2. But if we used the 4, we probably would have seen an even further drop in that signal. This is just for proving the concept that we can do it. And then there's a paper out on this also if you want to see more details on this data. So next, when the iFlex came out, we decided to take this dual reporter instrument, which can now do the 2 channels with what we call the RP1 or PE channel, and the RP2 or the purple channel, to look at more antibody isotypes that are reacting to the COVID virus over a time frame from infection. So compared to the FM3D, as the client said, when they saw this come in the lab, they said, this looks like a dinosaur now, based on the styling. And, they were wondering if we hired some Italian guy to design this. And well, that was before he got bought by Diasorin, which is an Italian company. So I couldn't, comment on that at the time. But, they were pretty impressed with the instruments. It's smaller footprint. It has a large dynamic range as well, compared to the, comparable to the FM3D. But the real advantage is also that dual reporter channel, the RP1 and RP2 channels. So when we got the instrument, what we wanted to do is see if we could take that whole assay as it's designed for the RP1 chemistry and do the same thing, but now we had to decide on what antibodies to use for the 2 channels. So originally we were using, that anti-human IgG that was biotin labeled with strepavidin, and we were playing around with different IgMs with different RP2 dyes, but we couldn't find IgMs that really bound that well as far as these anti-IgMs, or there was some cross-reactivity. And then because the IgM levels were lower, we needed to have a brighter signal. So eventually, after playing around, we came up with a combination of using the same human IgG in the first assay at the same concentration, but now instead of using strepavidin phycoerythrin, we're using strepavidin superbright. And then we shifted the PE channel over to using an IgM, anti-IgM that was directly labeled with phycoerythrin. But otherwise, we followed the same assay protocol. So we ran this on several hundred samples, essentially 544 with 300 unique subjects in that sample set. And then we looked at the titer from different days from symptom onset, from 0 out to 180 days out, for both IgM and IgG for spike again, the RBD, and the nucleocapsid. And as you can see here, the graph for M shows it, coming up, peaking and dropping down. And then the IgG is also coming up, as you would expect, pretty high, then levels off once you get out past 100 days. You see similar patterns for the RBD and something similar for the nucleocapsid. So we could easily detect in that same reaction what's happening in the profile for both IgM and IgG for all three of these antigens pretty easily without making any significant change to the assay itself. So the next thing was, again, can we do the same thing and see this ACE2 inhibition? So again, it was pretty simple, same assay protocol, just pop in this ACE2 incubation with the same antibodies we were using, for not doing the neutralization assay, and then start collecting the data. So what we see here now is we had to pick a smaller number of samples that we had good time course information on with regards to being either 30 days or less or 90 days and out from days from symptom onset, as opposed to looking at a whole population, because you wanted to see what was happening within groups of individuals rather than just a random population, what's happening in them. So what we can see for the IgM is that if you're inhibiting with ACE2, there's no real change in the level of the receptor, the nucleocapsid protein at either 30 or 90 days out. But if you're looking at, say, spike protein, okay, at 30 days out, there definitely is, a decrease compared to the nucleocapsid. And if you go further out to 90 days, it's even more of a decrease on spike with regards to IgM, generating some kind of protective antibody against those antigens. For the receptor binding domain, oddly, the decrease also occurred. It was lower than nucleocapsid, but it wasn't quite as far as it was for the spike antigen. But it still decreased significantly compared to nucleocapsid for IgM. For IgG, we did the same thing. Here's the 30 days out and 90 days out. Again, compared to nucleocapsid, the 30 days out was decreased, but not nearly as much as it was for the 90 days out. And then the same for the receptor binding domain. 30 days out, the IgG could be inhibited quite a bit with ACE2, and even more so after 90 days out. So this suggests that, again, as an in vitro assay for monitoring potential neutralizing antibodies, it works pretty good. It can tell you that we likely have that neutralization being generated, but we haven't really confirmed that with, say, a biological assay for these particular samples. But one of the things this also tells us is that, this kind of assay can work, even beyond COVID, because in this case, we have a pretty large antigen, the spike trimer, that has a receptor protein that is fairly large in itself and can block, pretty large sections of the epitope, especially on the receptor binding end. So this could probably be used for a number of other viral applications as well, not just COVID-19. So for example, there's a lot of hemorrhagic fever viruses for which various cell receptors are known. So the possibility of doing similar assays where you can get the cell receptor, look at a titer, against the specific viral antigens that will bind that cell receptor to titrate, your competitor in there and knock down the signal that you might see in that serum. It's possible with these types of viruses as well. And there's also viruses like measles, Zika, West Nile virus, dengue, and several others which could also fit into this category for using for this type of assay, which means that these assays are capable for looking at not only if protective immunity is generated, with regards to infections versus an immune response from vaccination, but for those who are developing, convalescent antibody serums or recombinant antibodies for different antibody therapies, could also be used to test the potencies of those as well. So while there's a lot you can do with the Luminex platform, some of the stuff you've heard here today with regards to genomic assays and a variety of other types of proteomic assays, the indirect serology over here is sort of one of the easiest ones to develop, but there's the capability of doing all these other things on the platform as well. So that pretty much sums it up. I don't hear anybody snoring. That's a good sign. So if there's any other questions, I'll be happy to take those now.